we're going to do the second part of section 10.7. Continue. Okay, today we're going to work on the surface integral vector field. Okay, there are a bunch of definitions that I want to go over. First one is the S is an oriented surface. If it is possible to choose a unit normal vector, and at every point x, y, z, so that n vary continuously over S. Okay. So here comes one definition. Well, we have another definition here. If S is a smooth oriented surface, then the unit normal vector is n is, well, most of you know how to get the normal vector from math 1C. It's the cross product of the two tangent vectors as or u cross or v, and then we want to divide this by the magnitude of this normal vector to get a unit normal vector. Yeah. Okay. One more definition. Definition. Now, here we have two of them. We have an upward oriented surface and a downward oriented surface. Well, upward oriented meaning that the normal vector pointing up. So here comes a surface. And these are the normal vector. So when the normal vector pointing up, we have a positive integral. And this thing, a lot of people would say flowing out. And then you're gonna see y flown out later in a bit. Okay, same thing here. So for downward, when you have the unit normal factor pointing down, then you have to put a negative in front of the integral, and then start flowing in like integral of vector field surface integral of vector field. Okay. So for the line integral, if you can remember, it is the work, and that will be F. That is the force dot T ds. The force is pushing a particle in the direction of the unit tangent vector. For the surface integral, we are computing, of course, it's going to be double integral over the surface. It's going to be F, right? But this vector field here, it would be pushing. If you look at the flow, right, flow in out, it is pushing fluid, flowing in the direction of the unit normal factor. So it's going to be N. And you guys can guess the last one. ds, then surface integral is the flux. And I'm going to explain to you guys what flux means after we get through the formula. Okay, so let's work on the formula that we already know. This one. So F is, of course, FRT, right? Because you got to parameterize the curve C. Okay, unit tangent vector or prime t over the magnitude of R prime t. The arc length is the magnitude of R prime t dt. Okay, now the flux should be similar. S, right? Okay, so here come F or UV. Unit normal vector is RU cross RV over the magnitude of RU cross RV. The surface area is the magnitude of RU cross RV dA. It's pretty nice, huh? And now you see some cancellation. So for the line integral, it's going to be F or T or prime T dt, right? For the surface integral, F or UV. It is the dot product, right? It's not the multiplication. It's the dot product, right? Because you dot the two factor. Or U cross or V. DA. Okay. Come the shortcut notation. F dot dr. And this thing, the shortcut notation is going to be F dot, well, you guys can guess it. DS. Okay. Well, you guys know what line integral does the computer work to move a particle along a curve C. Surface integral. We compute the amount of flow through a surface per unit of time. A lot of people would call this rate of flow through a surface or flux. Where F is equal to this vector field. And S is the hemisphere of radius 2 oriented downward. Oriented. A. You're gonna use spherical coordinate to parameterize S. And then B, well, hemisphere, so you can use rectangular coordinate to parameterize S. The answer should be the same. Well, most of you should be able to do this thing here. It's spherical coordinate. So x equal to radius is 2. So 2 psi phi cosine theta. Y is equal to 2 psi phi sine theta. And then z is equal to 2 cosine phi, where gotta get a boundary here. Phi is from zero to pi over 2 because it's only a hemisphere. Theta is, well, you got to do the full circle. So 0 to 2 pi. Yeah, so that's this. When we parameterize S, the R phi theta is this one. 2 psi phi cosine theta. 2 psi phi sine theta. 2 cosine phi. Này, Okay, so now we're just gonna do the substitution here. Now, row 2, so 4 sine square phi cosine theta, 4 sine square phi sine theta, 4 sine phi cosine phi. This thing a little smaller here. Okay, we have this. We have the R. We're just gonna do a f of R FR phi theta, because we need this one to do the. Actually, you can compute the dot product from here. It saves you time here. Okay, what do we have? We have a y, so 4 sine square phi sine theta, negative x minus 4 sine square phi cosine theta, 2z, so 2 times, oh shoot, I copy from this one. Y is 2 sine phi sine theta. Negative x is minus 2 sine phi cosine theta. And then 2z is going to be 4 cosine phi. A sine to 3 phi sine theta cosine theta. Minus 8. Oh, how nice. Oh, lucky. Oh, they're going to cancel each other out. And then last one is 10 sine phi cosine phi. Oh my God. This one is 10 sine phi cosine. Yeah. Okay. Now we can compute the flux, right? Flux here. Well, it's going to be a negative because we are oriented downward. If you can look at the definition here, oriented downward is flown in. So you got to put a negative in front of the integral. I'm going to explain to you this negative here. Actually, I'm going to use this color here, oriented. Oriented downward, and then double integral s f dot ds, negative, right? Parameter s. So it would be a double integral over the region D. We have f dot this one, 10 sine phi cosine square phi, and this one is the dA. We already have the region D because when we do this is region D. Oh, how nice. Yeah. Okay. We have the region D. Yeah. Negative 0 to 2 pi, 0 pi over 2, sin sine phi cosine square phi d phi d theta, and then this is going to be a negative 0 2 pi d theta, 0 pi over 2. I'm gonna put a number 16 outside here, or you can keep it in there up to use the same thing. Okay, minus 2 pi, and then this one is going to be a use up. Use equal to cosine phi. So the derivative of cosine is negative sine, right? And make sure you know that. So it's going to be a negative of 16 over 3 cosine to the power 3. Yeah. Zero pi over 2. Okay. So this one, pull it out. What do we have? We have a (32 pi over 3) and cosine q phi 0 pi over 2. I'm going to write pi over 2 like this. So that okay. 32 pi over 3, and well, cosine of pi over 2 unfortunately is 0. Right? Cosine of 0 unfortunately that's 1. So we have a negative 32 pi over 3. Parameterize S. Okay. Parameterize it. What do we have here? We have a equal x, right? Y equal y. Z equal, well, this is a hemisphere of radius 2 center at origin. So you can quickly solve for z. If you do x squared plus y squared plus z squared equal 4, then it's going to be a square root 4 minus x squared minus y squared. And for the region D, right? Oh man, you don't want to do the region D, not yet. Until you get to the integral, because you got to convert it into a polar coordinate. So called region D. As you can see, better to be dA, best to be all d or d theta. From here I can set up at 0 to 2, and then the angle theta is 0 to pi. Okay, we have to do this one. Let's say you still have to do the all x, y, and work it out the cross product. Right? Let's do it right here. It's not that bad though. y root of 4 minus x squared minus y squared. Right. Okay, so our x that with respect to x 1 0. Oh, what do we have here? With respect to x, this one is going to be a negative 1 over 2 root, and I'm going to work it out and I'm going to simplify, right? And then you got to multiply by minus 2x, right? So minus x over okay, right. Or y 0 1, right? And then similarly it should be minus y over 4 minus x squared minus y squared. And now we're going to do the the cross product or x cross or y. Let's see, what do we have here? We have a minus x over root of 4 minus x squared minus y squared. So it's minus, so it's going to be a y over root of 4 minus x squared minus y squared. And then the last one is going to be one. Okay, next we got to figure out the f of or x, y. What is it? Okay. What is f here again? Y negative x to z. Well, y is y, so it's going to be a y minus x, and 2z is going to be a 2 root of 4 minus x squared minus y squared. F dot or x cross or y. We have a xy over root of 4 minus x squared minus y squared minus xy. Yay, they cancel out. Yeah. 4 squared minus x squared minus y squared plus 2 root of 4 minus x squared minus y squared. And this is, yeah, 2 root of 4 minus x squared minus y squared. Same thing, right? Negative because oriented downward. Double integral f dot ds, right? And we parameterize s. So when we parameterize s, what we have is the double integral over the region D. 2 root of 4 minus x squared minus y squared dA, right? And then, oh, look at the region D here. That is the, where is the disk? So you can use polar coordinate. Zero to 2 pi, 0 to 2, right? 2 root of 4 minus r squared or d theta. Oh yeah, thank you. I forgot that needed because you have to keep it throughout the integral. Yeah. Okay. 0 2 pi. Oh man, I should have put a 2 out first. Okay. D theta 0 to 2 root of 4 minus r square or dr minus 2 pi. Let's see, what do we have here? U sub. The answer should be the same. U is equal to 4 minus r square. So we have a negative here. Negative of u 1 over 2 plus 1 is 3 over 2. So 2 over 3, 4 minus r square, 3 over 2. 0 to 2. Negative. Oh, 4 pi over 3. Let's see what do we have in here. 4 minus r square, 3 over 2. Right? 0 to 2. So 4 pi over 3. 4 minus 4 squared, that's gone. So it's just 0. And then the other one is going to be, well, you put in 0, then you're going to get a 4 3 over 2. Oh, what is 4 3 over 2 here? 4 pi over 3. Negative of 8. Oh, 8 times 4 32. So negative 32 pi over 3. If z is equal to, fx, y, right? This look like fx that, and this is like fy here. So next time you do this, it will be a little faster. Then or x crossed or y is fx fy1. Yeah, and this gonna cut your time down a lot.